Hello, everyone. My name is Leo Skada from University of Nevada, Las Vegas. Today, I'd like to welcome you for the first series of webinars describing the latest release of Gravitational Wave Transient Catalog, GWTC 5.0. In particular, we are going to talk about today the overview summarizing the core three papers. Before we dive in, a quick word on how these webinars are organized. GWTC 5 is an incremental update on GWTC 4. And because the release spans many companion papers, we're splitting it across several joint webinars. Today is the first one, the introduction, method, the results papers, describing what we observed and how. And we are going to start with a brief presentation about these papers, and later on move to panel discussion, taking questions from audience. So if you have a question during the talk, please don't hesitate to type that into Q&A section or verbally ask during the Q&A session later. Then on July 16th, there'll be a second webinar covering the astrophysical distribution and cosmology results. And that's where the population level inference lives. And tentatively on July 23rd, a third webinar on tests of generativity and the open data release. So if we point you to a companion paper today and say that's covered in a later webinar, that's the schedule that we are referring to. And with that, I'd like to pass that to Ed, who is gonna start off the presentation.
Thanks, Leo. Hi, everybody, and welcome to the webinar. My name is Ed Porter from the Astroparticle and Cosmology Institute in Paris. So if we move on to slide 3. So as Leo pointed out, today we'll be covering the 3 core papers. That's the introduction to version 5 of the Gravitational Wave Transient Catalog, the methods for identifying, characterizing events, and then kind of observations from the second part of the fourth catalog. So I just wanted to kind of highlight that this is a culmination of work by over 1,000 researchers, everybody from those who run the detectors to the people who do the detector characterization and calibration, all the way up to the analysts who run the different pipelines to extract the results that we'll prepare today. Move on to slide 4, please. Just to introduce our panelists for today. So I've already introduced myself. We have Vivian Raymond from Cardiff University and Leo Tsukada from University of Nevada, Las Vegas. They were the editorial chairs for the papers that will be presented today. And then we have Sanika Kadkakar, Lucy Thomas, Leo Zimmerman, and Eduardo Melotti from Pennsylvania State University, California Institute of Technology, the Institute of Two Infinities in Lyon, and University of Trieste in Italy, who will basically go through the different parts of the analysis. And on to slide 5, please. Before we get started, we just want to kind of talk about the philosophy of the focus papers. So the GWTC whatever number of catalogs are expected to be living documents. That means that each successive GWTC is a cumulative catalog. So in our case, GWTC 5 supersedes GWTC 4, and this will of course be superseded at the end of the year by GWTC 6. In the current round of GWTC 5 focus papers, we have the 3 papers being presented today. There's also the Cosmology Astrophysical Distributions Test of General Relativity paper. There's the O4B Open Data paper, and then there's one special event exceptional event paper, which was the GW24-1110, GW24-1011 paper. These will all form the GWTC 5 focus papers. So in some cases, the text is the same as it was for GWTC 4, but this is by design, and it'll kind of remain that way for GWTC 6, where we will increment on these papers again. With that in mind, I'm going to hand over to Vivian, who is the editorial chair for the introduction methods and the results paper.
Hi, everyone. So I was said I'm Vivian Raymond from Cardiff University. Let me go quickly through the introductions and methods paper. As was just explained, those papers are really incremental, and the introduction paper is the landing page for any reader trying to learn about the overall gravitational wave transient catalog, and specifically GWTC 5. But as a cumulative catalogs, it does talk through all of the previous catalogs that used event from the previous observing runs that you can see on this plot. It goes through a bit of an overview of the field, of the international gravitational wave observatory networks, some of the observing runs and the differences between them. This is where you will find a description of the observatory evolutions and references to the relevant papers that explains which improvements have been made, which hardware improvement have been made on the different observatory. This paper also provides a convenient review, of observed transient sources that we hope will be convenient to the reader. And this is not meant to be from scratch overview of everything, but it should cover all of the specific knowledge needed to understand the subsequent papers, and it contains a lot of references for the reader trying to move into more detail. So from this, we have a synopsis that presents a little bit what the rest of the focus issue for this GWTC 5 will be. And I do want to reiterate, this is an iteration on the gravitational wave transient catalogs, and as such, this transient, this catalog, this introduction paper will have a lot of overlap from the previous one. If you can move on to the next slide, we're going to go to the methods paper. And this is the paper that outlines all of the methods that have been used, keeping with the cumulative approach to those catalogs. This GWTC 5 methods doesn't just explain the methods used for this particular release, but does talk about the other methods that have been used to generate previous releases. The new content, however, is about all of the methods that were employed for the generations of the GWTC 5 results, which we're going to talk about in a second. It goes through all of the different aspects of the data analysis, in particular, from modeling compact binary coalescence signals, finding them, data quality vetting, the inference of the parameters of those signals, consistency test, data management, and so on. Here is just one of the figures of the papers showing our rough in box shape flow from the data to the data product that is being described in quite some detail in that methods paper. This is the paper that one should go to find the relevant references to the specific methods that were used, but this one provides an overview of all the methods together. And with that, I will leave it to Leo Tsukada to talk about the GWTC 5 results paper.
Thank you, Vivian. And I'll directly pass that to the other Leo Zimmerman, who's going to cover the search section.
Yeah, so hi, everybody, I'm Leo Zimmerman. We're working in searches, and I will present the result that we have for GWTC 5. So we will begin with some key numbers. We have detected 161 new candidates in O4b, with a probability to be an astrophysical signal over 0.5, which rise the total number of candidates from O1 to O4b to 390. And this number also includes the new results from the O4A reanalysis that is in GWTC 5. And if we look at the candidates on which we have run the full parameter estimation, we have 104 candidates. And if we go to the next slide, we have 5 notable candidates. So the first one is GW240925, which was a loud event that enables astrophysical calibration in the M4 detector. We also have GW240615, which is the best localized up-to-date event, I think with a localization roughly about 6 square degrees, which is super small. And we have also 2 candidates, the GW241011 and GW241110, which are 2 highly spinning BBHs with misalignment, and those two have a paper. And we also have GW250114, which is the loudest event up to now with an SNR about 90, which is huge. If we go to the next slide, we're going to see a table with the evolution of the number of candidates that we saw. So in 01, we have 3 BBHs, then 7 plus 1 BNS, then 41, then 31, etc. And GWTC5 with the reanalysis of offer A's candidate, we have 161 new BBHs, no NSBHs or BNS, but still we have a great candidate in the run. And if we go to the next slide, we will see the search sensitivity of the different pipelines. So roughly this plot means that if you observe in a hyper volume, so giga/q per year, you would expect with the pipelines to see, for example, if we take the plot at the top, 62 BBHs of roughly 100 solar mass, if we take into account all the different runs. But if we take only the O4B run, this number goes down to 26. But if we take the sensitivity of O4A plus O4B combined, we will account for 75%. So the sensitivity getting bigger and bigger. And I think that I will leave the rest to Leo.
Thanks, Leo. And I think Sanika will gonna take care of this parameter estimation part.
Hi, everybody. Thank you, Leo, for giving a nice overview of all of the events that we have detected in this observing runs segment. So as Leo mentioned, we had 104 events which have passed two criteria that we had, which is the false alarm rate should be less than 1 per year, and the astrophysical P astro, probability of it being astrophysical, has to be greater than 0.5. For those events, we have analyzed the waveform using different waveform models to obtain source parameters as well as extrinsic parameters like the sky localization, etc. This is exactly what we show in the two images which are attached on the right, and these are the 104 events that Leo was also talking about earlier. The 4 waveform models that we use to do this is IMAR Phenom XPHM Spin Taylor, SEO BNR V5 PHM, NR Surrogate NR Sur 7DQ4, and IMAR Phenom XPNR. So for all purposes, it's written up to 4 waveforms here because we have used 2, the first 2 consistently for all the BBHs that have been analyzed, which are the IMAR and the SEOB variants. But wherever applicable, and XPNR as well, and wherever applicable, we have tried to do NR Sur 7DQ4. So those are the different waveform models used. We also have different parameter estimation pipelines that we have used, and specifically in this GWTC analysis, we have introduced Rift along with the Bilby pipeline that we have always used for parameter estimation before this, as to run some of the parameter estimation analyses as well. And you can also find the details of this in the GWTC5 paper, for example. All of the key parameters like chirp mass, mass ratio chi effective, which is the effective aligned spin in the system, precessing, etc., and the precessing spin and the luminosity distance, etc., are presented in the figure on the right. The full posteriors are also available on GWASC, which is the Gravitational Wave Open Science Center data release that we have done. And this time, we have not provided any kind of mixed samples which combine different waveforms and the results that we get by using different waveform models for parameter estimation analyses. So if we can go to the next slide. So looking at specifically the source masses of the events that we analyzed, we have categorized this into source masses, interesting spins, interesting localization, or whatever we can find from this catalog. And looking at the masses, this spans more narrowly, this catalog spans more narrowly than GWTC4. What we mean by that is the minimum mass that we have reached is approximately 12.5, that's the median. This is for GW241109. And the max mass is 116 solar masses for GW241230. But the notable events that we want to direct your attention towards are, as Leo also mentioned before, GW250114, which is our loudest event so far. And owing to that, we also have the best inferred masses for 250114 as well. Then we have GW241011, which is a very well measured low mass ratio kind of an event. If I direct your attention on the plots that are present on the right hand side and you look at the lower plot, there is a dark green line and a light green line. The dark green line especially shows the lower mass event, which is roughly between 0.4 to 0.2 mass ratio, which is quite cool. And that's GW241011. Then if we look at GW240507, that is a low mass ratio event as well, but it also shows bimodality. That is something that is notable about this event. Amongst all of these events, there have been 5 events which have the remnant mass greater than about 100 solar masses. This means that this can be categorized as an or is very consistent with the categorization of an intermediate mass BH remnant. And we can, the way that we find these events are any event whose median of the remnant mass is greater than 100 solar masses. If we can go on to the next slide. Okay, thank you. So here we now also talk about the effective in spiral spin. As I was saying earlier, this just says the effective in spiral spin, which is chi effective, says how aligned is the total spin in the system with the orbital angular momentum, with 1 being maximally aligned and -1 being anti-aligned. And as you can see in the plot on the right, the y-axis shows the chi effective and the x-axis shows the chirp mass distribution. And we can see that, as with also other catalogs that we have seen before, chi effective is very consistent with being 0 for most of the binary black hole systems that we have observed. But we do have some events that we want to highlight. Specifically, we had 17 events which likely have a positive spin with 90% confidence. Some of these events are also highlighted in color in the figure on the right. But specifically, we have had two events which have a likely negative effective spin. You can also sort of find these events out on the right-hand side below the 0 line on the y-axis. These events are GW241110 as well as 241230, which likely have a negative spin. But we have an event which has a very well measured positive effective spin. You can also spot it on the right-hand side in the dark green color, lying clearly beside the rest of the population. And this has a very well-measured positive effective spin in our catalog. If we can go on to the next slide. So talking about component spins, they are poorly constrained in general, and that's what we also see in this catalog. But on the right-hand side, we have shown you a spin disk figure which shows the distribution of the component spins for a few handpicked events where we thought the spins might be interesting for you to look at. The notable events that we have are GW241127, where the primary spin might be anti-aligned. GW241011, the same event that we have been mentioning before as well, which has a misaligned, is consistent with having a misaligned spin, possibly from some hierarchical merger. We also have GW240925 and GW240114, which have a well-constrained in-plane spin, and you can also see this from the plot attached on the right. If we can go on to the next figure. So that was about the masses and the spins, talking about the source parameters, so the intrinsic parameters. Moving on to the extrinsic parameters like localization and how well we could localize events. For GW 10, 11, this was our nearest BB8 source to date, which is about 0.21 gigaparsec. For GW 1201, this is the farthest binary black hole source amongst the new candidates that we have, which was about 7.1 gigaparsec. And when we talk about sky area, I think Leo mentioned this before as well, GW 240615 is the best localized GW source that we have to date, which is about 6 square degrees. And we had 14 candidates localized within 100 degrees, square degrees or less. And the best localization in GWTC 4, as just a reference, was 110 square degrees. So this is an improvement over what we have seen in the last catalog. And that is all about the source parameters that I had to say. Passing it on to Leo.
Thank you, Sanika. And I think Lucy is going to talk about the systematics and so on.
Yes, hello everybody. So yeah, as Sanika sort of alluded to, both different waveform models being used and also different samplers can introduce systematic disagreements between results for the same events. Therefore, we can't definitively decouple systematics that have been caused by either different waveform models or different samplers. And in the paper and here on the slide, we present the 9 examples for which the systematics are most significant. And you can see that the differences for more extreme mass ratio values and Q in the second column from the left, and larger precession spin, chi-p, in the very right-hand column, are the most significant differences that we see in these systematics. If we move on to the next slide. Thanks. So systematics and other events that can either be astrophysical or instrumental, we can also unveil these by comparing the modeled signals with unmodeled reconstructions. And to do this, we use 3 minimally modeled reconstruction pipelines to reconstruct the candidates that we see, or I should say a subset of the candidates that we see. We use Bayes wave, and we use coherent wave burst in 2 different flavors. We have coherent wave burst 2G and coherent wave burst BBH. And these 3 minimally modeled pipelines differ fairly substantially in actually how they reconstruct the signal, but none of them find significant discrepancies with the modeled reconstructions of the actual signal. So you can see the results for all 3 of those pipelines on the right-hand side. And we don't find any significant differences in the distributions between the off-source overlap and the on-source overlaps for any of the 3. So this signals that we are not missing any significant signal content in our models of the signals. And I'll pass back to Leo.
Yes, thank you all for thorough presentation. So let me just wrap this up as conclusion, and GWTC 5.0 as 161 new candidates from O4B, bringing the cumulative catalog to 390 confident events since 01. The new candidates are entirely consistent with binary black holes, and unfortunately no neutron star related events from this run. And new release also falls in reanalysis of the O4A search results, which we label GWTC 4.1. And together, O4A and O4B now account for about 3/4 of the total search volume of the whole catalog. And of the new events, 104 pass our stricter threshold and get full parameter estimation inference. And a few of these are genuinely remarkable, some of which are also reported in a standalone discovery paper. For example, GW 241011 and 241110 are unequal mass ratio modules with well-measured misaligned spin, which might imply hierarchical modular candidates. And GW 250114 is the loudest signal we ever detected. with source property measured to unprecedented precision. And lastly, and not least, GW24 or 615 is the best localized candidate to date at 6 square degrees, and which indicates a direct benefit of having a Virgo detector back in the network. And before we move on to Q&A, I also want to acknowledge the people behind this work. As Ed emphasized at the beginning, a catalog like this is the product of entire LIGO-Virgo calcula collaboration. The detector commissioners and operators who deliver data, and calibration and detector characterization teams, and search and parameter estimation groups, and the reviewers who scrutinize every result. I also especially want to recognize the early career scientists, student postdocs, who do enormous amount of work like pipeline development, event validation, and day-to-day analysis that makes release like this possible. So much of what you have seen today rests on their work. And also, none of this happens without our funding agency. So I leave this extremely busy slide at the end and conclude the presentation. Thank you very much. And we are moving on to the Q&A session. And I already see one question from Peter in a chat. Why are likely positive effective spins more common than negative ones? Sanika, would you like to take this question?
Sure, and I would also call anybody like Lucy who would want to add to their answer on this question. But I think this question is not about how likely, I mean, it is about measurement precision in the sense that we are trying to exclude zero. Astrophysically speaking, there are more, if it's an isolated binary evolution, you would have aligned more chances of it being aligned. If you are dynamical, it's isotropically distributed. But there might be astrophysical reasons behind it. But this question is also of how well what is the measurement precision in my head? And that can be controlled. Sorry, I lost my train of thought. Just gonna take a step back here. What I'm trying to say is when chi effective is negative, in how I'm thinking about it is the waveform is smaller, it's harder to measure chi effective very well. With positive chi effective, there is a correlation with how good you can measure chi effective. And in my head, that's also what gives us more likely positive systems, which are both of these astrophysical reasons and also statistical reasons behind it. Lucy can go ahead.
Yeah, I guess I can just like add to the 2 points that you made that absolutely there are astrophysical and statistical reasons. But also I thought that we have a slight selection effect in that we are, because the signal is longer with a more positive chi effective, we're more likely to be able to detect those sorts of things out to further away. And so when we actually do population analyses, this is accounted for in the selection effect factors that are included in population analyses, which you can hear a lot more about in, I believe, an upcoming webinar about the populations paper.
Yeah, thank you, Sanika and Lucy. And I don't see any other questions, but please raise your hand too if you have anything from audience. Meanwhile, I can also kind of like want to trigger some discussion among panels, if I may. Right. For example, we talked about the waveform systematics. Maybe, and we said that we cannot really decouple between like waveform contribution and sampler contribution. Lucy, how can we go about that if we try to kind of like pin down how systematics really happening?
Yeah, this is a good question. And again, if anyone wants to jump in to add to my answer, please feel free. It was not always possible in this catalog because for different waveform models, sometimes we were unable to run with the same sampler or yeah, so sometimes in between two different analyses for the same event, there would be both a different sampler used and also a different waveform model. Throughout the process of doing the parameter estimation, we were doing consistency checks. For example, we made use of the Dingo code to sample using the SCOB NRV5PHM waveform. And also we made use of Bilby MCMC as a sampler in cases where we needed to double check in some cases of systematics. Yeah, but as I say, it wasn't always possible for every event, in this case in the catalog. However, in any places where the discrepancies were more than sort of numerical error, then these are plotted in the plot that you saw on the slide and in the paper.
Thank you. That makes sense. Right. Let's see if there's any other question. Peter asked another question. Thank you. About machine learning assisted validation and inference cross checks. Where's the line between ML being a speed up tool and ML becoming part of scientific trust chain? That's interesting question. So Peter, would you be able to elaborate the question? So are you saying like asking whether we are using ML for both reasons or either? Maybe I'd like to understand what you meant by speed up tool as opposed to scientific trust chain.
Can I maybe jump in? I think I
Sure.
okay. So I think this is a great question, and this is not something that is specific to gravitational astronomy in general. Right now, we are moving towards using machine learning more and more as it's proven to be very capable. As some of the problems that we have, it's proven to be very good, algorithms, but also able to leverage the next generation of computational hardware in a way that is very hard to pass. However, most off-the-shelf, dare I say, commercial machine learning applications are very good at getting to 95% accuracy. If you think of most of the applications, getting the answer to the text correct 95% of the time, identifying that it is a dog instead of a cat in a picture 95% of the time, it's great for all intents and purposes. However, and this is where we can use some of that for inference cross checks and learning assisted validations, as you phrase them. Where we tend to struggle a little bit is moving from 95% to our standard 99.99999% level of accuracy. So the way this is going there is right now, until we reach that level of accuracy, which is very difficult to do, machine learning seems to be almost only, and I should be careful with the words here, the field is moving tremendously fast, but it is almost only a speed up tool, knowing where to look or having an initial guess, which then allows us to use our more standard, dare I say, more trustworthy techniques on a much smaller part of the parameter space, or with a much better initial guess, which we can then refine with more expensive methods. So I guess the line right now is simply that the pure machine learning approach doesn't quite have the accuracy that I require. So that's where we draw the line, at least for the methods as used in GWTC 5. So even our top of the line, cutting edge machine learning approaches right at the end of their analysis chains, they will go back to analytical, computationally well, tested calculations of, say, the likelihoods or the mismatch or the parameters. They are now able to do it a lot faster because since they use the machine learning pre-processing to know what to calculate, they don't have to spend as much time exploring big spaces. But at the very end, we still don't fully trust the accuracy of the machine learning approach. This is a bit of a long-winded answer, and I hope that answers part of it. But to finish, I would say that while this is true for this GWTC 5, not only are things evolving very quickly, but we're also looking ahead beyond GWTC 6 to third generations and beyond for gravitational astronomy, where standard methods will rely more and more on machine learning, and by then machine learning might become more and more trustworthy. But that's the state of it as far as I understand in my own application of it. But I would be very happy for others in the panel to disagree.
Yeah, thank you, Vivian. I know like there's been some tools they're using like deep learning that can like detects the data quality anomaly, and we have been using that in an established way. But I think with the improved accuracy or advancement in machine learning in general, I think we are kind of pushing that toward more like scientific results. And I know there's been some work for parameter estimation, for example. I'm not sure if anyone who does parameter estimation wants to say about any machine learning technique that's been worked recently. I see hands up. Eduardo, are you
Yes,
going to chime in?
would like to add something about machine learning because it is such a varied field that, for instance, deep learning may not be part of what we do, as in the case of the unmodeled methods that were mentioned at the end of the seminar. In that case, there is a very well-established method which is used and which is based on decision trees, which is well understood from the statistical point of view. And so that is quite reliable and we use it routinely. So I don't know what the question was meant, actually meant, if Peter meant some basic well-tested methods or the more general deep learning methods that are used nowadays. But at any rate, at least part of the pipelines do use machine learning methods to with good results.
Yes, that's a good point. ML is broad term that can be interpreted in kind of any other way, and I agree that also search pipeline has been using like classic machine learning technique that learn stuff from the data in the past and predict what's in the future. Ed, you want to say?
Yeah, I just wanted to say that machine learning is being used more and more, especially in parameter estimation. But as Vivian said, I think one of the issues at the moment is the philosophy of development outside of the scientific community compared to what we're actually doing. So first of all, there's the accuracy issue, as Vivian said, going from 95 to 99.99%. But I think there's also kind of the philosophy that the off-the-shelf machine learning packages are basically assuming that you're prepared to run for weeks, potentially months, to get to that 95%. Whereas at the moment, we're trying to do things, on the kind of level of hours to days. And I think there is a bit of a gulf in the kind of off-the-shelf development with kind of those timescales in mind. But, as we move forward and as the packages become more advanced, then we may see a convergence between accuracy and runtime compared to what we have today and what we'll need for kind of scientific inference in the future.
Yeah, thanks for the thoughts, and that's a right point. Um, Let me see if there's any other question. Thank you, Peter, for asking questions. That's been a great discussion. I also wanted to maybe raise a point that well, it might a bit step away from ML, but like so far we have been only talking about compact binary system, whereas in theory there might be some, uh, like sources that emit like generic burst like signal in short transient or could be long transient. And um, maybe Eduardo, who is an expert on like those unmodeled signal like search or characterization. So do you want to say anything about it and the ongoing status of unmodeled search recently?
Thank you, Leo. Yes, the search is going on. Unfortunately, it is not yet in the catalog because we have not yet detected any pure burst source, but the hunt is going on. We look for sources like, say, supernova signals. This would be really a big achievement, being able to see a supernova signal. They are predicted to be extremely weak because of the near spherical symmetry of the explosion, but they would be exceptionally informative from the point of view of our understanding of the models of supernovas. Except for that, there are many other sources that could produce burst signals. Among them, for instance, cosmic strings, or in general, topological defects in the cosmos. That could also be a great achievement, being able to see those signals. And then there are other, maybe even more exotic sources where you have relativistic jets that could also produce in a different way a non-zero quadrupole moment and therefore also gravitational waves. So we are still trying to see those signals. We are employing methods which are different from the ones that have been described in the previous discussion and which make the core of the catalogs. And we do hope to be able to report about some of these exciting and fascinating events in the future.
Thank you, Eduardo. Can't wait to see other exciting events in the catalog. All right. I also like to open the floor for any discussion that panel wants to make. Also,
Yeah.
questions.
I
Yeah, please.
would basically raise the I'm like looking at the results from GWTC 5, and I'm going to put Leo Zimmerman on the spot here. Where are all the neutron stars gone? I'm like, no NSBHs, no BNSs in GWTC 5. Is this a problem with our pipelines, or is this the universe is just not cooperating?
I would say that the universe is not cooperating. Now, I know that we had a lot of significant online NSBH events, but that were retracted at some points. But I would say that that's how it is. We just didn't detect DNSs or NSBH, even though they are the one that we're really looking for in the pipelines. We care more in a sense because that's the kind of event that we detect less. So we really try our best to detect them, but just they happen to be less here. So yeah, the universe is just not that cool with us.
Yeah, I'd like to also jump in for that. The detection algorithm of search pipeline is a little bit complicated, and we are kind of like, for example, one of the CBC search pipeline GSLL, which I've been working on to develop, has some like pre-calculated weights to detect between BNS and NSBH, BBH, and that like relative weights across different categories is kind of like something that we come up before the run, and now we are getting like way more BBHs than BNS, so we kind of like might be able to revisit, tune the search pipeline to, kind of like correctly assign those weights. Not just because we have an BNS or try to kind of like boost them up artificially, but it might be also sign of further optimization we could make for the pipelines. There's also, I'd like to say that there's another field of development in search pipeline to make like inverse follow-up campaign. In the case of GW17 OS17, for example, we detected the GW event first, and they produce the external alert to electromagnetic community. But the other approach would be possible. For example, if like electromagnetic community can give us trigger for EM transient like GLB or kilonova, we should be able to kind of like set up another separate search around that trigger time, and and also direct the search to particular location on the sky. And that kind of like offline targeted search has been conducted during the collaboration, though we didn't see any extra BNS event with that, but we are still keep pushing that approach as well. We are also trying to make that even like medium or like low latency, so that we can do like the inverse follow-up almost real time. But such development is still ongoing, so a bit of work remains to be done. But I'm looking forward to more development in that regard.
Excuse me, Leon. Maybe we could
Yes.
Tell our audience something more about the huge effort which is implied by the analysis work, by the numbers that we eventually produce in the catalog, because people usually don't see the effort that goes into that. I mean, all the people involved in peer analysis do a lot of work to obtain those numbers and to interpret them. Maybe we could say something more about that. I mean, the panelists from the P community are very well quite able to explain that. I mean, it's not just a simple macro chain Monte Carlo. It's more than that, and it takes a lot of time and effort.
Yeah, I guess from search side, it's not just we run one analysis and call it a day and go to the beach with a cocktail. We always like some weird thing comes up, and sometimes we might get weird signal that don't look like signal, but it might end up being significant, and we have to kind of like not in a biased way, but try to kind of like understand why such thing happening, and try to follow up, for example, almost every single candidate that show up, and double, triple check the sanity of the results. I think Leo Zimmerman agrees as well, but you can also chime in if you have anything special to mention.
Nothing comes to my mind. I think.
Well, maybe there's something about the selection of waveforms, because there is at least one waveform, if I am not wrong, which is there just to keep into account the possibility that there are non-general relativistic effects, isn't there? Among the waveforms that were listed at the beginning.
Oh, so you mean for parameter estimation?
Yes, exactly.
Right. Maybe Lucy might be able to comment on that, how like waveforms are chosen. And I think some of them are different from GWTC4. So there's some like technical details might be involved. Lucy, do you have any comment on that?
Yes, so the choice of waveform models used for this catalog is slightly different to the previous one, and that is to reflect the fact that our waveforms are constantly being developed, and lots of people are working very hard to make sure that the models are more accurate and incorporate more of the physics that we know happens within general relativity, because these are waveform approximants, and we're trying to get as close as possible to the full general relativistic effects. So 2 of the 4 have been updated. That is the IMR phenom XPNR and SEOB NR V5PHM are new or updated with respect to the previous catalog. All 4 of the models are completely only assuming GR effects and nothing beyond GR. And also they reflect developments in speed-ups of models as well, because I guess alluding to the question before about the amount of time and effort that parameter estimation takes, sometimes some of these analyses can take days to even weeks, and sometimes we have to rerun them, sometimes multiple times. So that's also reflected in the choice of new models. Yeah, I hope that answers your questions.
Thank you, Lucy. Seneca, do you have anything else that you want to add about how hard you worked on this?
I mean, no, not really, but I would just like to say that we do have pipelines which automate parameter estimation and which are thought to be completely independent of human input once they are set up. Like, you don't have to keep a track on them, and they just run and the PE results are produced. But I'd like to highlight what Lucy said. Some of these runs go on for weeks. Sometimes they are kicked off from the cluster. These are small computational things that a team of 4 analysts, which was led by Lucy also, we did all of that, and that's sort of the effort that goes on, even beyond analyzing just the results, just getting to the results computationally using the nodes, making sure that one of the 64-second events that we analyzed was running for weeks on end, and we were just waiting for the results to come out before we could analyze anything. And that required the most amount of effort. We also implemented a whole new PE pipeline this time, which was also pretty cool. The Rift pipeline that we included to verify results from Bilby. That was also super cool to see that the results that we have been producing for the last catalogs with one pipeline can also be verified with another one. And that just increases our confidence in the kind of results we put out as a collaboration. And that was also quite cool to see. So those were the points that I want to add.
Thank you, Seneca. And no hands up, but also we have some. Oh,
There's a question in the chat from Shantanu.
yes. I was gonna say that. So Shantanu is asking whether localization shouldn't depend on the number of active detectors. If so, then what was the best localization possible? Because many detectors were simulating active. Maybe I'll take that for as in terms of searches. I think that yes, that was done by 3 detectors. It was a main reason because it was localized, for example, as small as 60 square degrees. But also other factors like detector sensitivity itself is a one of the major factor that improves the localization. So, for example, there are, I think, a couple of events seen by Hanford and Livingston only without Virgo, but they are so sensitive that SNR is like 30 or even more. And they, in the case of best localization in O4A, for example, it was localized as small as 110 square degrees. That might sound like still big numbers, but it's pretty small relative to, for example, in a much bigger banana shape, SkyMap inference that's more common to detector case. Does anyone want to add on this?
I may add something, Leo.
Please.
Just to give the impression of how much the signal to noise ratio matters, you can think of the noise spectrum of the detectors. The larger the signal to noise ratio, the larger the extent in frequency of the signal itself in general in our representation. But a large frequency band means a small time uncertainty because of the uncertainty principle. And this means that the sky localization is improved by this small uncertainty in timing, because the lower the signal to noise ratio, the larger uncertainty in timing, and therefore the worse localization. So having a good signal to noise ratio gives a good localization.
Yes, indeed. Yeah, thank you for the more thoughts on this. If no other additional comments, we can take another one from our, I think, colleague from Hanford Observatory. So Corey is asking why we had a day where there are 5 detection, which was June 21st and June 30th. So I think it's well, first of all, does anyone want to take this question? Vivian?
Yeah, I mean, obviously, thank you for the question, Corey, and thank you very much for all the work you're doing at the Hanford Observatory. Couldn't help but notice that on both those days, the Livingston Observatory had a higher duty cycle and a higher inspiral range. So there, of course, I'm joking. So the real answer is it's just Poisson statistics, right? In terms of what we get and the number of detection that we get. However, those 2 days, I was just playing around with the detector status web pages, which are public, by the way, for anyone who wants to have a look and see which day what detector was on. What's interesting for those 2 days is they are definitely among the ones that have very good range and very good duty cycles across the network. All 3 detectors were on for a long time with a good, stable sensitivity. So you would naturally expect that those are the days where those things tend to happen. However, beyond that, I am not aware of anything specific of June 21st and June 30th that would have explained why there would be that many. Those are, the Poisson statistical fluctuations. But if you can identify some days, some correlations between which operator is on and the range, the observing range of the detectors, that would be kind of interesting. We definitely need to have some kind of a prize system for the highest duty cycle and the highest range. So yeah, I know this is a bit of a disappointing answer. I wish they would have a very specific answer for why those, but it's because on those days, the job of the observatory operators were just awesome. As they should. Thank you very much for that. Yeah, I'm glad it is, because I mean it really does take a lot of people for everything to happen, and it does start with the detector. So thanks.
Yeah, thank you, Vivian. If I may say from search side, also each search pipeline has its own like weekly or some regular shift among several developers or operators, and like everyone we have kind of mixed feeling that it's awesome to have many detections, but we might not want to have as many as 5 detections in a day and keep being busy. So but it was great to have such a days. All right. I
Maybe
don't see.
since
Oh,
there's no other questions, I would just offer a bit of a reflection to everybody. So we started this adventure in September 2014 were just the one detections, and we're so happy. And then 3 months later, we had another one, and that was great. And then we had a catalog because we had two of them, so that's all we needed. And now we have the detectors have gotten so sensitive, the operation is so stable, the detection methods are so accurate. We have days when there is 5 of them at once. I mean, we can all see the trend, right? So it sounds like we should be fully aware of how much the field has gone forward and how much it still has to go, because this is quite a change, right? From chasing the one detections to now days when there is 5 of them. So sure, it's a lot of work, but I hope there will be soon days when there is 10 of them, and then days when there's 100 of them, and days where there's so many that they are all overlapping and it's a mess, and it's going to be beautiful discoveries.
Yes, thank you for great reflection. And it makes me think that we can like have to sort of like shift change the way we think about detections or catalog, like as it goes to like hundreds to thousands. We probably, this what we are doing in this way doesn't scale with that. So like we have to kind of like be mindful about how we can automate things, or make as little human intervention as possible. And that might be the next goal to think of for the upcoming catalog in the future. Is there any other comments from other panels? And I think we have taken all the questions, and we're passing the hour, so that might good time to wrap this up. This webinar. Getting back to the slides I'm sharing, I'm just to remind people that upcoming webinars for next week about astrophysical distribution and cosmology. So please keep that in mind and put that into your calendar. And I'm looking for seeing some of you next week. And I think that's a good time to call it. And I'd like to thank everyone who joined today and the panels, and a huge thanks to Casey Sloan, who has organized this awesome webinar as smoothly as it could. Thank you, everyone. And Casey, if you want to say anything at the end, please go for it. Otherwise, we can maybe close the session.
Yeah, congratulations to the panelists, and thank you for a wonderful talk.
Okay, I'll stop sharing.